I guess it will be somewhere around 9 o'clock by now. So let's start the day. Welcome again. A slightly different subject, the .NET API. And in this case, we're going to talk a little bit more about the more advanced features of the .NET API, which is basically also a little bit about the structure of how we set up the .NET API. As the author of the .NET API, so my name is Ewout Kramer. I work for FHIR NET API. And you might have guessed I'm a software developer. And most important for today is that I'm the lead developer of the .NET API. And creating an API has been a learning experience, I must admit. Because creating an API is something different than creating your own software where you can change everything at will. Most of us love changing our own software. I did this 2 months ago, but it's not good enough anymore. Let's pull it out and do it again. You can't do that with an API because you'll break your interface. So I've learned a lot about interfaces, and also we've been doing the API since ESG1, so it's about 5 years old now. And while building it, you know, we started with ESG1. FHIR looked a bit different back then, and so the whole API is actually kind of a work in progress, and we're constantly changing and refactoring the motor. Luckily, we have lots of unit tests, so I hope most of you don't normally see that we're changing the internals of the library. But I do want to talk about what's happening there and what are the current internals of the library. So first, let me start out with the structure of the NuGet packages as they can be found in NuGet. The core library, of course, is called HL7.5 core. This is where it all started, all the way back from ESG1. So this has the generated classes, so a class for every resource in the specification. And if you download the source code, you would find currently some T4 templates, and if you run them, they create the classes for you. They actually read structure definitions and then generate the C# classes, which means that some of you have done that. That if you tweak the structure definitions there and rerun the template, you get a whole new set of C# classes, not necessarily compatible with the FHIR standard, but anyway, you could do that. So that's in there, and then there, of course, there is the serialization and deserialization classes, the FHIR parser and the FHIR serializers. They take the FHIR XML and JSON and turn them into these in-memory local classes. Well, assuming you used the library before, or you followed the beginner's tutorial yesterday, I'm just hoping that you've seen those. And finally, of course, having POCOs and XML and JSON data doesn't really do anything until you can use the HTTP protocol as specified in the specification. So there is an HTTP client in that same core as well. So that's most of the time that's where people start out working with creating a few classes, sending them out to the world, doing a query, and so on and so on. Split up of that is a library called HL7.5 support, which has some of the utility methods, and everything that does not is not specific to a FHIR ESTU version. So these libraries don't have anything like the domain classes, no patience there. They're totally insensitive to changes to the FHIR specification. But they're used by all the other classes. Separate from that is a thing called HL7.5path, which contains the FHIRPath evaluator. And as you can see, this is not an accident. The word FHIR is not HL7.5.FHIRPath, and that's because the FHIRPath library is supposed to be written independent of FHIR. So you should be able to use the library on different object models, which I've never tested. So in practice, probably there's some dependency there, but that's the idea. Getting a FHIRPath statement compiled and then evaluating. And then there's the specification library, which adds on top of all of that access to the definition. So if you want to get to a structure definition, if you want to get to a value set, terminology service, and maybe most important, profile validation. I'm going to talk about profile validation tomorrow, so I won't spend a lot of time on that today. So in FHIR support, well, I want to start talking about element model. Element model is at the base of all the serialization and deserialization, actually almost everything. This is the glue of the library. Element model is an abstract representation of FHIR data, so independent of FHIR, of XML and JSON. If you went to my FHIRPath tutorial yesterday, I already talked about it, that this is one of those things that we really did not have when we started out with EC1. This is something that we gradually introduced in the library. Because working with POCO classes is nice, but what if you're building a tool that doesn't care about the EC2 versions, or you want to just extract metadata, you don't want to parse the whole thing into a precompiled POCO class, or if you want to read incorrect data so you can correct it. So what we've done is we created a lower level set of parsers that have a logical model of FHIR data which is independent from the precompiled FHIR classes. So you can access both EC2 and EC3 data. You can imagine that in simple FHIR, people can just upload all kinds of crap to it, and we will still try to mine the metadata from it, and then say, oh, actually, we don't really know what it is, but it looks like a structured definition, or it looks like a value set. This was in the FHIRPath tutorial yesterday. This is the abstract model. So we represent the element model on the lowest level in the library represents FHIR data as a tree, starting at the root with, say, patient, and then name if you have a repeater name element in your instance. So this is a patient instance with two name elements, and active, and each of these nodes has the name, a type, and probably somewhere finally a value. So if you have an instance with patient.name.use is official, you will have this tree representation in memory of that data. And as you can see, this is abstracted away from the actual format XML or JSON. This is represented in code, of course, in the library by an interface called Element Navigator. So name, type, value as visible in that tree, and there's an added property called location, which looks like patient.name1.family.0, which is nice because many times when you're navigating around an instance, it's good to be able to display when you're debugging where you are in that tree. And then you can move through the tree by methods like move to next, which will move to the next sibling, and move to first child, which will move to the first child of the tree. It's a very basic interface. And finally, clone, because as you can see, this is a navigator, so this is a pointer within the tree. And if you want to stay somewhere in the tree, but you want to go left and right, you clone this thing, and then you can go to other places in the tree. We added a few extension methods on top of those to make navigation easier. So if you want to use this very low-level interface, you create an XML DOM FHIR Navigator with some XML text, and then you can say navigate to my children called name, then navigate to my children called given, and then select the value as a string. This is on the lowest level, but the more high-level parsers do. So in the end, of course, on top of this, something is built that reads this into POCOs, but this is at the lowest level. Now, what's important to realize is that this interface is used everywhere, not only in the parsers, but it's used in the profile validator, it's used in the FHIRPath evaluator. They all run on top of Element Navigator, so they don't assume serialization format. It also means that if you manage to implement this simple interface on top of your custom object model, the FHIRPath evaluator and the validator will still run on top of it, and will be able to even serialize your data. So currently in the library, Element Navigator here at the core, and it has 3 implementations in the library currently. One that works on raw XML files, one that works on raw JSON files, and one that works on objects in memory. And this is, of course, how validation is done. Since validation, where is it? The validator here uses Element Navigator to validate. You normally, if you validate an in-memory instance, you create a patient, and the library has this POCO navigator, which will adapt such a POCO class and implement Element Navigator. So this way, the validator navigates through your POCO instance. You can do the same thing on top of XML or a JSON file. And this is used by the parser and the serializer the validator, and the compiled expression and FHIRPath as well, as it said. So if you're using the higher level part of the libraries, and you're using the POCOs, this is actually what happens. You have your XML text, for example. The library creates an XML on FHIR Navigator, which implements Element Navigator. Then the FHIR parser uses Element Navigator and then reads the contents of this abstract tree into your POCOs. You manipulate your POCOs, and then the reverse happens. All the POCO classes patient encounter in the implemented Element Navigator via the XML FHIR Navigator. And there's a Navigator XML writer that then writes the stuff in text. You don't normally see all of this because this is hidden behind the normal XML and JSON parsers, but this is what happens internally. So what we have not done, because it's all pretty recent, is that you can now start manipulating this tree before it gets serialized. So if you want to implement summary functionality on your server, which means that you only, the underscore summary property of the FHIR HTTP spec, so you can do only does a subset of the serialization. So this just filters out a few elements from that tree and only passes on to the XML writer those elements that are part of the summary definition of that resource. You can imagine you can do all kinds of cool things, filtering out stuff based on privacy rules, and before all of this gets into the serializer.
Ewout,
yeah.
The navigator on the right should be a POCO navigator.
Yes, this should be the POCO navigator. This one. Yeah. Absolutely correct. So that's a bit of the internal of how we deal with data. And Element Navigator is paramount. It's very important to realize that once you get that implemented, all the other infrastructure parts like the validator and the parsers and everything start working on top of that. Another feature is parsing huge bundles. So many times we get bundles with thousands and thousands of entries. Of course, you can just parse it into a bundle POCO, but that will create an enormous bundle POCO in memory, while all you want to do is enumerate over these entries. You don't need that whole bundle in memory at one time. And to do this, we have created a JSON and an XML Navigator stream, which is actually an enumerator. So it has a Element Navigator current. So this moves through the bundle one by one, just by doing move next, move next, move next, move next, move next. You'll get to the current entry in the bundle. And the current entry then, of course, is an Element Navigator. So on the lowest level, you can parse these huge bundles by going over the entries one by one, and then you get this Element Navigator. The current, feed that into the POCO parser, and you can get a single POCO at a time if you want, or you can just dive straight into the Element Navigator and pull out metadata or whatever you want. That's the process here. The bundles scan sequentially. We've tried to make this as efficient as possible, low memory footprint, and we've implemented a very efficient seek as fast as we can on top of the .NET framework. So this uses XML reader below to as efficiently as possible navigate through this XML or JSON. So this is below, and I wanted to show you what happens when you just use normal POCO parsing. That's in the core library. Now I like to move to the specification library. The specification library allows you to get access to structure definitions, value sets, operation definitions, and so on. It's distributed as HL7.5 specification, ST3 or DSU package of NuGet, and it contains a zip, specification.zip, with all the data produced by the FHIR tooling. Well, not the human readable data, but all the structure definitions and so on. So it packages viable profiles, resources, profiles types, extension definitions, HTML search parameters. These all contain the value sets that are with the spec, and even the XSD schemas and schematrons. And you don't have to go out into that zip, unzip it yourself. No, we wrote an API to do that for you. So all the conformance resources are in there. And as you probably know, all conformance resources are identified by a canonical URL. So that's the unique ID of any of these resources. So if you want to reach out to the structure definition for patient, that's http FHIR.org, h7.org/FHIR/structure definition/patient. And that's the key to accessing this data. So how are you going to resolve this if you have this and you say, okay, please give me the structure definition for this? Well, the spec says that you should be able to go out with any FHIR client to this URL and get the data. But you know, your application might be offline. I don't know if it's a good idea whether to do that, so most likely your application will want to try to find that structure definition somewhere close to your binary distribution. In this case, for example, the specification.zip, that's already in the NuGet package. So you could compile it in your apps, you could store it in your database. These are all probably the ways we foresee that you will have this conformance information somewhere near in your application. We've created a very flexible system to get to the data. And there's another interface here that's important, that's called iResource Resolver. So iResource Resolver is an abstraction that says, resolve by canonical URL, whatever URI, and I will return you back a resource. So you can imagine that if you pass it a structure definition here, you get a structure definition back. If you pass it the canonical URL to a value set, you get a value set back, and so on. And the current specification part of the .NET API has a few implementations that come with it. Most prominently among those, the zip source. So you can guess what it does. This implements iResource Resolver on top of that specification.zip. So you do resolve by canonical URL, and then the library takes care of you unpacking that zip only once, zapping through the whole bundle and everything that's in there, and trying to locate whatever conformance resource you need based on that canonical URL. But we also have an implementation called directory source, which will do exactly the same thing, but then with materials that are not in the zip, but in a directory. For example, a directory where your application runs and where you keep your own custom structure definitions and so on. Finally, there's a web source which does actually go out on the web to fetch that canonical URL. And we have two more abstract resolver. One is called the cached resolver. You can guess what that does. This implements this interface on top of another resolver to cache access. So you don't want to go out to your directory and do your zip every single time again. You only do that once to increase your performance. And then finally, there's a multi-resolver which you pass a list of iResource resolvers, and so it will try them one by one. So you can then combine and match within your application on how your application will get to your specifications data. Maybe you have a database with structure definitions that go with your application. And in FHIR server, we have that. If you implement iResource Resolver on top of that, and you combine that with the ones that we supply you, so here's a zip source which reads through the zip and the web resolver and a multi-resolver on top. So when this multi-resolver, which implements the interface, is asked to resolve a canonical URL, it will first try this one and then go out to a cached resolver. The cached resolver says, well, I don't have the canonical URL, or if it has it, returns it immediately. And if it doesn't, it will go out to yet another multi-resolver. And the multi-resolver then says, well, I'll try the zip source first, and then the web resolver. The net effect of this is that if you try to resolve the URL here, it will first try your database, and then a cached version of whatever is in the zip or in the directory of your application. And you can mix and match and write your own implementations of iResource Resolver. Yeah?
Is this something that is created due to a specific need you have experienced, or because you're trying to think abstract of what could possibly be needed?
Yes, if you create an API, you don't have to only think about yourself, but of course also of others. But in fact, it is being used now. For example, in Simplifier, if you use validation on Simplifier, it tries all the structure definitions in the Simplifier registry database first. So the Simplifier team has written this on top of their database, and then they fall back to whatever was there. So this mix and matching is something we really see happening. Another implementation you could do is one that actually goes to compiled resources in your executable, for example, if you do that. We didn't write that, but you could that too. Yeah. So this is the kind of flexibility that we imagine. Well, you can read that at home. All right. Next in the specification libraries is terminology support. I'm not going to say a lot about it, but we have a built-in terminology server. And there are two resources concerning the terminology in FHIR, the coding system and the value set. And without going into too much depth of the value sets normally contain lists of codes, but they could also say, well, I'm a value set composed of that value set and that value set. And in the .NET library, there is some code to actually read these value sets and create the full, as we call, enumerated extension of value set that contains all the codes in a value set. So the only thing you have to do then to see whether a code is a member of a value set is do a code lookup within the value set. So the main functionality we provide in the .NET API is to read value sets, even if they're composed from others, and then you can do a code lookup within those. This can be done in memory for simpler value sets, but if you have more complex needs, you have to go out to one of the existing FHIR terminology servers. And again, you see here that you have multiple options, so you can see where I'm going. Where is it? We've created an interface called iTerminology service, and that can be implemented by multiple implementations of a terminology service. There's only one operation currently. It's called validate code, and we have this is in the wrong order. We have several implementations of it now in the spec. One of them is let's see. Let's get over this. Yes, here we go. One of them is the local terminology service. This does an in-memory expand and lookup. So it uses the functionality provided in the .NET to get value sets, to expand those value sets, and then to find the code, and does all of that in memory. There's also a class called external terminology service, and external terminology service uses a FHIR client and goes out to a real terminology server. Let's be sure, this local terminology service, that in-memory one, is not nearly as powerful as you would sometimes need to use the full power of value sets. If you follow one of the terminology sessions here during these 3 days, you can see that you can do all kinds of wacky things with value sets. And I'll promise you, the local terminology service doesn't do all of that. Luckily, there are some companies who are providing real terminology services, and they are exposing these services using FHIR. So there is an external terminology service, which is a really thin wrapper implementing that interface that goes out to such terminology servers and then does that code lookup. And then, of course, there's a fallback terminology service, which first tries to do stuff inline, in memory in your application. And if that fails, says, okay, then now go for the slower option, which is go to the outside world and use the external terminology service. This is what we normally use. There's no way our local terminology service can do everything. So as soon as this reports that it's too complex, the value set that it has, we will fall back to the external terminology service. Where are we in time?
17 minutes more.
FHIRPath. Yesterday I talked about FHIRPath and what FHIRPath, how you use FHIRPath, but of course we need a way to run FHIRPath. And the FHIR specification, no, that's not true. The FHIR, there's this, I showed you, there is a NuGet package called FHIRPath that actually implements both compiler and evaluator for FHIRPath. HL7.FHIRPath and NuGet. And as I promised, this is built on top of that Element Navigator. So it theoretically should work in any object model that implements Element Navigator. As FHIRPath is not FHIR specific, this is important. if you implement Element Navigator on any object model, you'd be able to run FHIRPath invariants and FHIRPath queries on top of your object model. The FHIRPath support in .NET consists of two components. One is a compiler, and the other one is the executor actually. So the compiler that contains a parser, parses your FHIRPath statements and turn it into a thing called, well actually you do two things with it. You can compile it to an expression, or you can compile it to a function. The compiled expression is actually a delegate in .NET, and so it's a function that you can then call. So that's purely done for efficiency. So given the FHIRPath compiler here, you ask it to compile a FHIRPath statement, it will return you a .NET function that you can immediately call then to evaluate that FHIRPath statements without having to parse the FHIR expression again and again. So this is very efficient. Compile expression is a native lambda that will run the statement that it has just compiled against the Element Navigator. If you want, for display purposes or anything else, code analysis, you can also compile the FHIRPath statement to an expression tree so you can analyze it. And Brian probably has a talk of his own at this moment, has created kind of a .NET, a lightweight .NET application that actually shows you the parsed expression tree of the FHIRPath statement. So how to use it? Simple, you create a new instance of the FHIRPath compiler, and you say compile this very, very simple statement, patient.name. Then you run that validated sheet, so it returns you here, this CE is actually a function. It's a callable C# function. So you call here CE, and the argument is, of course, a pointer to wherever you want to run it on. In this case, this is this Element Navigator. And then you get, as a result, a set of Element Navigators. And that's because patient might have multiple names, so this will always return you a set, one for each name returned. And the Element Navigator in this case will represent, of course, the human name at that spot in the tree of the patient. Not always you want to work with Element Navigators, you don't always want to work with this low-level library. So we have written on top of that a set of functions that make it easier to do the same thing on POCOs. Well, I explained to you that to turn POCOs into Element Navigators, you use the POCO Navigator. You see it in action here. So given a patient that I want to run the statement on, I create a new POCO Navigator, which implements Element Navigator, and then I can run the FHIRPath statement on that navigator. You could run this function immediately on that Element Navigator, but we've created 3 extension methods that, depending on how you want to use it, might be more appropriate. So if you are sure that your FHIRPath statements returns a single primitive value, you can just run statement.scalar and you'll get an object representing the primitive value. If you just want to know whether the result is true or false, you can run the extension method as Boolean. So patient.active, for example, if you compile patient.active, you could better run ce.isBoolean and you get a true or false effect. Okay. Just like the regex compiler in .NET, this will compile and cache the last 500 or so expressions. So if you use that, you see you're never here. You're not creating any FHIRPath compiler or anything. You're just creating the POCO Navigator and then running the function scalar on top of this. This will actually internally compile this once, store and cache the compiled expression in a static, and then return the result. And the next time you run it, it will use that compiled state. To make it even easier, I mean, is it nice to see that you can do it this way, but to make it even easier, we have provided yet another set of extension methods that go on top directly of the POCO object model. So you can do patient P something and then field color. And it, you know, this internally, of course, uses this, and this internally finally will do the compilation and run the state. So that's bottom up. Depending on whether you're using POCO model, you're probably just going to run your statements like this. But if you want to have more control over caching, you'll have to do the more lower level interface, compile the statement yourself, store them wherever you want, and run them yourself. Then there's a few hidden gems that I just want to point out in the FHIR NET library. One of them is resource identity. I've seen a lot of code using my .NET library, and many people use a lot of string concatenation to work with these REST URLs. HTTP my server /FHIR /patient /something. Well, in fact, we've created a class called resource identity, which is a subclass of URI that helps you work with these URIs. So one thing you can do is easily build one by saying, build me a resource identity consisting of patient, identifier, and maybe even optionally a version identifier, and this will then just create the URL for you. It has some useful methods like giving the URL for the canonical URL for the FHIR defined type human name, and so on. Even more useful is it will parse those for you. So if you have a URL that looks like this, then you say, create me a new resource identity based on this URL, and it will split up for you the resource type, the ID, and so on. So, you know, all that concatenating and parsing, it's right there in the library for you. Extension manipulations. We all know about extensions, and every class in the FHIR library has a property called extensions, and a property, well, and if it's available, a property called modifier extensions. On top of that, we created a few extension methods to make working with them easier. So, one thing is probably you're not only interested in, well, the spec and the serialization format, and so the POCO makes a distinction between modifiers, modifier extension, and extensions. But sometimes you just want to work with all of them. You want to see, do I have extensions at all? So there's an extension method called all extensions, an extension method called get extension, which will search through all of these and find the extension with a given canonical URL. So if you put extensions there in the data, you see them. The easiest thing you can do is say, for example, patient.name.getExtension my extension, and you get the extension back. Now, extension itself is a data type, which then has a value, which you then have to pass to whatever you know that is the value of that extension. So if you have a simple Boolean extension, you still find yourself writing code like patient.active.getExtension yada yada dot value, oh crap, and cast this to a Boolean. So instead of doing all that, there are a few extensions methods to make it easier. It's actually, the word extension, the fact that we in C# we have extension methods now, to get to the extension methods is quite quite confusing. But let me just say, we've added these methods for you to get to the Boolean extensions, giving it a certain canonical URL, getting to a string extension to a string-based extension, and getting an integer to go to these integers. So these are, these are just helper functions to help working with extensions. Of course, there are setters, adders, removers, and so on. But you don't have to manipulate the dot extension and dot modifier extension lists yourself. Anyone working with the POCO model for some time probably will have had the need to put your own private annotations on them. One example that you might use it for is, say, you fetch an observation. Observation somewhere has a subject. The subject is a reference to the actual patient. So you go out with the FHIR client, or wherever you go, and fetch that patient. Now you have two objects in memory, but you'd really like the one to point to the other. What you could do is create an annotation and say, I want to make a private, this is my private bit of space on any of the elements in the POCO. You can make your own private annotations and say, well, actually, this reference point to this object that I already fetched into the file. Or maybe you want to keep track of whatever fields in your POCO have been changed by the user. Well, all of this you could do by subclassing the existing classes and the existing data types. It's way easier to use the annotations that we have available on. So all the parts of a POCO in the .NET API has methods called set annotations and get annotation. And here I have elaborated a little bit on what I just said. So say that I want to keep track, if I fetched data from a FHIR client, I want to keep track on what was the last moment that I actually fetched it. So I want to annotate any resource with the origin, where did I get this resource from, and when did I retrieve it last. So presumably you could check that and say, you know what, if this is older than an hour, I go back out and fetch it again. This, of course, has no place in a serialized format like FHIR. This is really a private annotation. So what you do, you create a class with these two properties, and then you create methods. That's why I do. This is my best practice. Let's say subject of annotation, subject of set annotation data, or subject of annotation here with this type to get them. So say a resource. If you do resource.annotation with this type, you will get your private annotation as stored in this class. And if you want to set the annotation, you could say resource.set annotation with an instance of your data. We've copied this approach from Microsoft. This is not really our idea. Initially, when I thought about creating this, I thought I'd make a dictionary with a key and your private annotation. So you get a key origin and a private annotation, a key retrieved when, and then a datetime offset. But then I looked at the Xdocument and Element implementations of Microsoft, and I saw that they had used this, and we thought it was pretty brilliant. So you always, when you want to make your annotations, you create a class of your own, and then you set the annotations and get the annotations based on the type. So it's still a dictionary in some way, but you don't have a string key. The type here is your key. Pretty smart what the guys at Microsoft did, so we just blindly copied that. Then there's a class called Transaction Builder. And this is used inside the FHIR client. The Transaction Builder helps you build a bundle which contains a transaction. I don't know if you all know about this, but you can send a whole set of FHIR gets, puts, posts, and so on in one go using a bundle and transactions. And the class Transaction Builder helps you create such a transaction. So you can say, create patient P, create patient here, create patient P. Then I want to have the resource history of patient 7. I want to delete patient 8, read, and then to bundle. And this will create a in-memory bundle creating these statements. Internally in the FHIR client, I'm using this every single time you do FHIR client.read, FHIR client.update, FHIR client.whatever. I create a bundle with just this one statement and then send it to the server. But this is a public class, and it's just as well as you would use it to create transactions. Right.
Is this an atomic transaction then?
So that depends on the server I'm sending it to. But the specification says that transactions should be atomic. Well, actually, transaction has an element in the spec where you can say, well, this is just a list of statements. Try whatever you can, or really, I want you to treat this as a transaction. Of course, then it's up to the server whether it can implement that. But you will be able to create a transaction at least. Yeah.
And if one fails, will this then roll back the other transaction?
So what would happen is we create a transaction here on the FHIR client. We send it to the server. The server, if it sees that if it's well implemented, if it sees that it is indeed a transaction, will try to execute your transaction. And if it doesn't work, the server will return an operation outcome on the HTTP request. The client, the FHIR client, will pick up that operation outcome and then if you've sent this transaction builder B here, you would use the FHIR client to send it by doing a post, and the FHIR client will then throw an exception, giving you access to that operation outcome. So that's the whole U-turn that happens. You create a bundle here, you use the FHIR client to send it to the server might do it or don't, return an operation outcome, and if that's a failure, the FHIR client will raise an exception and inform you of that fact.
But none of the other actions in the bundle have
Sorry.
let's say the create, in this example, the create here fails.
Yeah.
Would the delete and the read, they would not happen either.
That wouldn't happen.
Okay.
Yeah, if the server is well implemented. Yeah, yeah. And we should hope so. Otherwise, you should look for another vendor. Yeah. Any more questions? So, since all I could do here, of course, is point out the basic parts of the spec, I've created a few exercises, and I will, and those of you interested, we will find our table and sit down and actually try out whatever you've picked up here and you think is interesting and worth trying out. So I would invite you to really use my time to ask all of your questions about this. I have made a few suggestions, some exercises what you could try. So if you're interested in getting to the specification tip, so getting to the structure definitions, operating definitions, you could do this exercise. I know they are also provided on paper, but
they are on the FHIR DevDays website as
on the
well.
FHIR DevDays website as well.
Just FHIRDevDays.com and click on the exercise menu and find the Ewout store.
Yeah, because here's are the paper ones, but these
yeah,
are
but
mine.
if they run out, you can
Ah,
just
there.
download the PDF from the website.
And if you'd like to practice implementing iResource Resolver yourself, I have a small suggestion here that we try that on top of a list of value sets, and you implement an iResource Resolver that is actually just in-memory resolving this on a list of value sets. So given a canonical URL, this resource resolver would just list, zap through the list. If you want to work with the technology server, I have some suggestions here, what you could do. And but that's, you know, if any of the things that I just discussed are of interest to you, and you think this was just a few slides, can I know a little bit more about it? Can I just try it out? Just join me to the table, and we'll take a look at it. All right, that was it. We're on time.